Hello viewers, welcome to the lecture on automated machine learning and network science for the social graphs. So to start with, let's have a question. So do you know that the social structure, or you can say the same conceptual framework applies to many of the problems in social world. So for example, be it product recommendation on Amazon, or a friend suggestion over the Facebook, or maybe bot detection on Twitter. So all of these, they rely on the same concept, that is complex networks of human interactions. And this is basically what we call the social graphs. These social graphs, they generate a huge amount of data. So when it comes to social graph, the data is of two types. It can be like the profile centric data, or it could be the graph centric data. So profile centric data is basically the data that is associated with the people who are creating their profiles on the social media. And whatever interactions they are doing, whatever actions or activities they are doing of liking and sharing the posts or reposting someone else's post. So these, they create the graph type of data, or we can say the interaction data. So for that, we need network science, network analytics to be applied on the social graphs. So that is how the network science and the social graphs are connected. Now let's understand how automated ML comes into the picture. So the machine learning is basically for predictive analytics. So there are a series of machine learning available, but many of them are not suited for the graph structure data. So we have to identify first that which kind of machine learning model, or let's say a set of machine learning models that are applicable for a particular network or the social graph given to us. So when the graph is a very large scale one, when we have large number of nodes and large number of interactions, then building ML models from the very scratch and manually coding the hyperparameters and the features, the pre-processing part, it becomes really very tedious. So to ease this, as well as to make it a rapid execution, the AutoML frameworks comes into existence. So this AutoML frameworks, or automated, when applied with the network analytics to the real world social graphs, they create knowledgeable insights of predictive analytics on these kind of graphs, which are nothing but the human interactions. Now we have had a little bit of knowledge on what network science is from some of our previous lectures. But just to review that it is a interdisciplinary area. And in this interdisciplinary area, what all things that comes, it is about understanding the complex systems, having a little bit of mathematical knowledge, and also some underlying graph structure and the network topology. So these prerequisites are required when we want to understand network science. And a network is what? It's a collection of nodes, or we can say vertices, and these vertices, they represent the physical world entities. Those can be people talking to each other over the social media, or it could be the devices that are communicating through each other through the wireless media or something. And then we have the edges, which are the interactions. They signify certain kind of relationships, or maybe some associations. And these network science, you can say the techniques, they reveal basically the patterns and the different structures, the behavior of the complex interconnected systems. So patterns means like what kind of pattern is followed when the communication is going on between multiple profiles, or what kind of behavior the nodes are showing, whether they represent themselves as hubs or the receivers of information or relaying the information to other nodes. So, what is the behavior of the complex nodes in those kind of systems? And structures could be like the whatever the underlying network framework is, whether it is a static one or it is a dynamic, that is, it changes over time. And by analyzing these kind of network along with nodes and edges, we analyze the network topology and different types of features. So, when it comes to the network structures, or synonymously you can call the graphs at the stage, they have certain additional features along with the profile features. So, this could be the network topological features, the edge weights, or the directions associated with the edges, that is, who is sharing certain posts to whom, like that. So, the directivity is also important, and then if there is a sentiment associated, then we can have the signed edges also. So, whether there is a negative sentiment or a positive sentiment, then that can be mentioned. And if it is a dynamic graph, it means that it gives an impression of the growing network. So, there are different types of network instances available. It could be the social networks, the biological networks, different types of web pages connected over the internet, and also the intranet in some cases, transportation networks, and many more. So, how in a social graph, let us say very specifically how the social network is constructed. So, there could be different people with several profiles across social media. So, data can be taken from the social network, or you can say multiple social networking sites, from the physical world, that how they are moving, the devices, they can also give some information to us. And then they apart from having their accounts on the social media portals, they may be having their personal blogs also. So, all these blogs, the real world and the social network, they are all giving us input, some kind of data with some features, some interaction details also. So, all these things are integrated, or you can say aggregated into data sets, and these data sets, they are stored in the large scale databases, and they have multiple features, be it profile features or graph features, and these features are then analyzed along with the network science techniques and also with the machine learning models to get knowledgeable insights from out of these graphs. Now, how to represent these networks? So, they can be represented using different types of structures available. So, if it is a kind of a growing network, then we can have some time varying graphs, or maybe some simple or multi graphs. If it is a static, but there is a change of links between the existing nodes. So, different types of graphs are also available that can be used to represent the networks. And different types of social graphs are there, like the social network itself, or it could be the ego networks, or sometimes the networks of the social media bots. And also we often see these days that there are echo chambers that are created over the social media. These are nothing but very closely built communities of some people who are talking over a particular topic in a great detail. And sometimes the truth and the falsification of the news needs to be verified, and hence these analyzing these communities, these echo chambers becomes very important. Then comes this term, the social graphs. So, the social graph, as of now you have got some idea that it is a kind of quantifiable measures that we can take out from the graph and use some visual representations to see how these social online social platforms rather, they are performing, and they also have these kind of digital interactions with them. And also these social graphs, they have evolved a lot in the very recent days. We can see that people have their profile not only on just one social media profile, but across many social media profiles. And there are also some educational portals also. They open up as discussions and forums, collaborative codings, and also they have this ample number of social media portals for different purposes. So people are very much engaged these days with the social graphs. So when there is so much widespread of these social graph usage, then number of analysis or demand for analytics regarding these graph based networks becomes essential. For example, to finding out the influential individual nodes, or maybe which are the communities that are strongly connected or maybe weakly connected, or which are the pair of nodes rather that are strongly connected to each other, forming strong ties, and vice versa as the weak ties as well. Or we might be interested to see how the information is flowing, if we want to track it down, and whether the information that is flowing is correct or it is misinformation. And if it is a misinformation, then which are the profiles that are propagating these kind of falsification news across the social media. So certain kind of privacy or and many other things that are against social security, some vulnerabilities are there, they can be also analyzed. So how these things are analyzed? They are analyzed using different types of measures that the network science domain offer. So it offers the centrality measures, so a wide number of centrality measures are available, and we have discussed these in some of our past lectures. And also there are algorithms for detecting the communities, and then we are sometimes also interested about is there any homophily existing in the social networks. So inherently it does, and when it does, we want to see that are these similar users, they tend to connect more frequently, and if yes, then on what kind of topics they are more communicating with each other. Then it could be the link prediction, or it could be tie strength prediction, or how the information pattern is there, what is the rate and the span associated with the information outreach. So there are also some challenges that are associated with this social graph. We know that social graphs are very large, they are realistic, and they generate the profile centric and also the graph centric data. So what are the challenges? It is basically revolving around the sparsity of the connections, more importantly, because all the people on the social media platform are not connected to each other. As a result of which, when we are storing the information, say for example in a matrix format, then all the nodes are not connected to other nodes. Hence, a lot of zero entries will be created, null entries will be created, because there is no edge between each of the pair of node. Okay. So when there are a lot of sparse entries in a matrix representation, then it becomes very difficult to model kind of machine learning or some network based learning model. Also, when the network is really very large, the computational complexity for any of the kind of problems that we were talking about, like link prediction, community detection, or centrality computation, etc., it becomes very expensive. And what else? It becomes really difficult also at some times because of the sparsity and also of the immensity of the size of the network, that how to select the appropriate machine learning model that is suitable for a particular type of network. So these are some of the challenges that we usually face in a case of social graphs and analyzing them. Okay, and there are some other issues also, because these social graphs, they are real instances. So most of the time we have heterogeneous connections existing. So sometimes it is not the simple graphs that can represent the information associated with the interactions and all that are going over the social graphs. So sometimes we may go for the multi-level graphs, the knowledge graphs, multi-graphs, etc. And the temporal dynamics is again one more challenge, and also the growing network, because this growing interactions, it's inherently present in the social graphs. So the growing network has also certain challenges associated with itself. Now let's understand what are the advanced aspects of the social graphs, because we have to apply automated machine learning framework. Okay, and for that we need to identify, along with the profile centric features, what are the advanced features available with respect to the graph, so that we can have some topological details along with the profile centric data. So some of these advanced aspects could be the growing nature of the graph itself that we were just talking about, and also there is something called power law behavior, and also a phenomena that is prevalently it's prevalent in the social networks, that is the 6 degrees separation. So let's go one by one. The growing networks. So mostly we always do not have this realistic networks, real streaming networks, which we can see that how it is growing. So to simulate those kind of networks, we have some random networks with us. We can statistically generate them just to see how the networks, when they tend to grow, then all those kind of network analytics like the centrality measures and link prediction, community detection, diffusion, etc., they can be executed over the growing networks. So to understand the growth of the random networks, we need that whatever model we built, it should simulate the realism, the real world network, okay, the real world behavior that usually is there associated with the real social networks, okay, and also the heterogeneity part and the dynamism part. So some of the instances could be the scientific network, the citation networks, the web pages that connect to each other, and also the online societies, online blogs. So everything on which the user or the people, they tend to participate online, they form a kind of social graphs and have certain social interactions. And let's see how this growing network implementation is done. So this is a code snippet using Python programming, which you can implement, and you can yourself see that how the growing network actually happens. So in the real world it happens in a way, and here we are simulating the real world networks and using the synthetic networks and statistical distributions to get an you can say an impression of how a network grows. So the code starts with some of the import statements. We import some libraries. So we import the network X for the network analytics part. Then we have the matplotlib and the time. Now when we do import time, it means that we want to introduce some kind of delays so that you can see properly that at each instant of time how the graphs are generated. And then there is this interactive mode associated, so that again the interactive mode of plotting can be visible to us. So let's say we are starting with initial nodes equal to 3. So there are initially 3 nodes or 3 people starting, say for example a social network or a social circle of discussion, and we want a total of 20 nodes by end of our simulation time, say t. And we assume that whenever a new node enters into this closed community of initially 3 nodes, they tend to form 2 new existing nodes. So, this keeps on repeating till the end of simulation time is achieved. And then what happens? We start creating the graph. So, in this case, we first create a complete graph. So, nx dot complete graph. Nx is here the reference to the NetworkX library. So, we are calling the complete graph method from NetworkX library and giving it the initial number of nodes, which is in our case is 3, and then we are giving also a kind of positioning. So, there could be different types of positioning libraries. We are using here the Spring layout. So, different other layouts are available. And then we are drawing the initial graph. Now, we are drawing the initial graph and we are keeping the node color as light blue and the edges as grey. So, you can use your own color set also. And then we can give the title and also a pause of 1 unit of time. And then we actually start simulating the growing graph. We have a small for loop here that ranges between the initial nodes, that is 3, and the total nodes, that is 20 in our case. And the edges, they keep adding as a new node enters. 2 edges will be added to the existing nodes in a random manner. And for this we are using the Barabasi-Albert network, or you can say the graph, and this iteration, it will keep going on till the end total amount of nodes are completed. Okay. And once all these things are done, what we will do? We will plot the graph. Okay. So, for this what we have the nx dot draw again with all the labels as true, so that you can see for yourself that which node number is being plotted currently, and again the same thing, the node color and the edge color you can specify with a pause of again 2 time units. And when you execute this code, you get this kind of a output. So, we start with a 3 node network, then gradually 1 node is added with 2 more connections, another node is added. So, this keeps on going, and finally you can see that at the end you get a big network with all those 20 nodes that we wanted to reach out to. So, this gives an impression of how the growing graph is implemented using Python. Okay. So, you can have more than 20 nodes and you can have your own growing graph, and at each stage of the growing graph you can have your network analytics applied. So, this way the network science over network that are growing in nature can be applied and can be examined. Now, the next one is the power law behavior. Now, this is another behavior that is associated with the social networks, where we often see that it is a kind of basically a relation that in which one variable tends to vary as the power of the other. Okay. So, it looks like a graph where there is a kind of heavy tail, and you can see here on the screen that Px is the probability for observing a value x, and alpha is the positive constant, which we often call the power law exponent. Now, there are some properties associated with this. It is the scale free nature, okay, and the another one is heavy tail. Now, let us understand what are these properties actually refer to using a diagram. So, heavy tailed are often people get confused with the light tailed and the exponential tailed distributions. So, let me explain it to you. In exponential distribution, what happens? The tail of the exponential distribution, it very quickly converges to 0, while the heavy tail distribution, it will take a lot of time to actually converge to 0, and sometimes it does not converge to 0. Because the heavy tail distribution, they actually refer to several real world cases. Okay. So, for example, the number of hubs on the social network. So there are only few nodes that are considered the hubs of information or the influential profiles on the social media, but there are others profiles that exist on the social network, though they are not influential. They may be having 2 or 3 friends, or maybe a set of 10 or 20 friends, may not be 20 million, but they exist. As a result of which, the heavy tail distribution, they tend to merge on a very lighter note. So there could be some examples like the social network, as I was saying, the degree distribution of the nodes could be one example. Also the word graphs are also one good example, where there are very few connections, or you can say very few words that are that exhibit the scale free nature, and they are frequently used words, you can say. So on the screen you can see that the word frequency graph of say content which shows the feedback of a economics professor. So there are very few words that have maximum kind of occurrences, but most of the words, they have very less occurrences. So we will continue this discussion on power law behavior and other advanced aspects of the graph, and thanks for watching. Thank you.